All right, before we start with class P, talking about more rational functions, I wanted to give you guys one example of some polynomial division, because we are going to need to use that to find the slant asymptote of a function. So how do we do this division? So you could write this way, x cubed minus 8x plus 7 divided by x plus 3. We're almost never going to actually write it that way. The more usual way of writing division is like this: x cubed minus 8x plus 7 divided by x plus 3. Oh, and I've actually divided it by the wrong thing. Well, we'll do this. We're not going to get the exact answer I'm looking for. That's all right. I meant to divide by the other piece, which I've now forgotten what it was because I was writing this problem when I was thinking about it earlier. We'll still do the division. It's good practice. So we're going to divide x cubed minus 8x plus 7 by x plus 3. And when we're doing polynomial division, if you're missing any powers of x, like I'm going from x cubed to x to the first, I really want to hit every power in between. So I'm going to add in a 0x squared just so I'm not missing that term to make my life easier, really. You don't have to do it, but it's going to make it easier if you do it that way. So then when we're doing this division, it's like regular division. Like if I was doing something like, I don't know, 63 divided by 4, I would be like, how many times does 4 go into 6? And then I say 1, and 1 times 4 is 4, and then subtract. And 2, and then bring down to 3. And then I say, what do you multiply by 4 to get 23? And I say, well, 5 is the biggest number I can pick. And then subtract, and then my remainder would be 3. The same idea is going to happen here. We're going to look at the highest power in each of the things and ask ourselves, what do you multiply by that to get that? What do you multiply by x to get x cubed? X squared. And then we're going to say x squared times x is x cubed, and x squared times 3 is 3x squared. And then we're going to subtract. So people like to do this thing where they change the signs. I just like to write a minus with parentheses. Either way is fine, whatever works for you. X cubed minus x cubed is 0x cubed. I usually don't write that term. 0x squared minus 3x squared is minus 3x squared. And then we do the whole thing again. We bring down the term, and we start with a negative 3x squared minus 8x. And we ask ourselves, okay, what do you multiply by x to get negative 3x squared? It's going to be a minus 3x. Minus 3x times x is minus 3x squared. Minus 3x times 3 is minus 9x. Subtract. That minus that is 0. I'm not going to write it down this time. Negative 8x minus negative 9x is really negative 8x plus 9x, which is just x. Welcome. Thanks. And then we bring down the 7. We do it one more time. So what do you multiply by x to get x? I know it's kind of a boring question, but x times 1 is x. We're going to put a plus 1 up there. 1 times x is x. 1 times 3 is 3. Subtract. And x plus 7 minus x plus 3, the x minus x is 0. The 7 minus 3 is 4. So that's the process of polynomial division. You just keep asking yourself, what do you multiply by the highest thing out here to get the thing there? We're going to see more examples of this. This is a slightly more complicated version of what we're going to be doing, but it's not so complicated that it's not worth seeing. Yeah, that's a part of the process of graphing the next few rational functions. It's only part of it, though. So, questions? Feel like you guys, yeah, Eric. So here's the thing. We could totally do more with this, but the thing we're going to be doing with it doesn't require that. So yes, you could definitely, if you wanted to, rewrite this rational function, x cubed minus 8x plus 7 over x plus 3. And this will be something you will want to do when you take Calc 2. You might want to rewrite this as the quotient, x squared minus 3x plus 1, plus the remainder divided by the divisor. That's something we do with this. It's not something we're going to do today, but it's something you can do with these things in the future. And there is a good reason to. Other questions? Okay, let's get into it. Graphing rational functions with slant asymptotes, also called oblique asymptotes. I never knew they were called oblique asymptotes until I got taught this class. I was like, oh, slant asymptote, sure. Also called obliques. A rational function has a slant asymptote only when the degree of the top is bigger than the degree of the bottom by exactly 1. So the bottom could be degree 3, sorry, the bottom could be degree 3 and the top could be degree 4, or the top could be degree 7 and the bottom could be, well, I can't say the word, could be degree 6. As long as the top degree is exactly 1 larger than the bottom, you have a slant asymptote. That's the only time. Any other situation, you will not have a slant asymptote. And then the slant asymptote is going to be a line, and it's going to look like a line with the form y equals mx plus b. A lot of them are going to be like y equals x plus something, or y equals x minus something. You can make it more complicated, but they're usually not. And to find slant asymptotes, I should be looking at my, I'm like, where are my notes? Yeah, to find slant asymptotes, we're going to do polynomial division. So for example, if our function was say, yeah, let's actually get it right this time. X cubed plus 4x squared minus 2x plus 6 divided by x squared plus x minus 3. We're going to do the top divided by the bottom. So x squared plus x minus 3 divided into x cubed plus 4x squared minus 2x plus 6. And then we're going to ask the same sorts of questions. Let me zoom in a little bit here. A little bit easier stuff. What do we multiply? So you really want to write these polynomials in the standard way, where the highest power is first and the powers decrease as you write it out. So you definitely don't want to write this as like x minus 3 plus x squared. That's going to screw things up. Same deal here. So what do we multiply by x squared to get x cubed? X. And then you do x times all of this. So x times x squared is x cubed. X times x is x squared. X times minus 3 is minus 3x. And then we subtract. X cubed minus, so the first term should always be 0. Right? When you subtract those first terms and you don't get 0, it means you picked the wrong thing to multiply by. So x cubed minus x cubed is 0. 4x squared minus x squared is 3x squared. And negative 2x minus 3x is negative 2x plus 3x, which is 1x. And then bring down the 6. Okay, now pay attention here, because I'm going to show you how to do the least amount of work possible for this. What do you multiply by x squared to get 3x squared? 3. We're done. That's all we want. Once you get to the constant term up here, that's it. Y equals x plus 3 is the slant asymptote. And you really, really can and should stop there. You could do more work, right? You could say 3 times x squared is 3x squared, 3 times x is 3x, 3 times negative 3 is negative 9, and do the subtracting and get x minus 3x is negative 2x, and 6 minus 9 is plus 15. But you don't need any of that. So all this stuff in red I wrote over here is completely unnecessary.
Why do we not do that?
Well, because that's not, so we're not looking to write this, we're not looking to rewrite this. Right? We totally could rewrite this. In fact, let me go back to this other page, piece of paper here, just so I have the room here. If you really wanted to, you could rewrite x cubed plus 4x squared minus 2x plus 6 over x squared plus x minus 3 as the quotient x plus 3 plus the remainder negative 2x plus 15 divided by the divisor. Here's what's happening with this. So let me actually back up for 1 second. I mean, we'll look at this. We'll continue to look at this for just a sec. But I want to ask all of you a question. For this function, y equal to, let's make it not terrible, 2x plus 1 over x plus 3. What's the horizontal asymptote? Show me on your fingers. Okay. See. You can't, so I feel like some people are trying to do like a negative. That's the vertical asymptote, is negative 3. The horizontal asymptote is going to be y equal to positive 2. And the way we see that quickly, right, exactly, yes, is because the degrees are the same. We're looking at the quotient of the leading coefficients. Now, I'm going to talk more about why that's true, because we should. So let's do the polynomial division. It's going to be real short, but let's do 2x plus 1 divided by x plus 3. What do you multiply by x to get 2x? 2. 2 times x plus 3 is 2x plus 6. Subtract. 2x minus 2x is no x. 1 minus 6 is -5. Okay, but look what we can do now. We can rewrite 2x plus 1 over x plus 3 as the quotient 2 plus the remainder over x plus 3, the divisor. Okay, here's the point. If x gets really, really big, what's going to happen to this? It's going to get very small. You're going to have -5 divided by an infinitely large number. So this part here gets smaller and smaller and smaller as x gets larger and larger and larger. So here's the thing I want you all to see. This function, 2x plus 1 over x plus 3, gets very, very close to 2 plus 0 as x gets really, really large. That's why 2 is the horizontal asymptote, because the function is getting very close to that particular value as we move way out that way or way out to negative infinity. And this function, although I don't know exactly what it looks like, I know it has a vertical asymptote at -3. There's a horizontal asymptote at y equals 2. And would have a y-intercept at 1/3. An x-intercept at -1/2. It would look something like this. And as x gets very, very large, the y values are getting really, really close to 2 and just a little bit smaller than 2, right? If this is right, if x is a really big number like 997, this is going to be 2 plus -5 over 1,000, which is just a little bit less than 2. Okay, so the polynomial division tells us this. It tells us that, oh, this part here, this remainder part here, doesn't have a lot of meaning to us. It's not that important. So if we look back here at this example, this remainder part here doesn't have a lot of meaning as x gets large, because the denominator is going to outpace the numerator. Right? The denominator is going to get really, really big because it's got an x squared in it. The numerator is not, because it just has an x. So this is going to get very, very small as x gets very, very large. And this part here, the slant asymptote, is going to be what the function gets closer and closer to. So it's not going to be a horizontal asymptote. It's actually going to be a line looking slanty like that. It's going to be a slant asymptote. And the function is not going to equal it, but it's going to get closer and closer to it, just like it would for a horizontal asymptote. Okay, we're going to do some examples for sure, but I really want you guys to kind of hopefully take that, is that this is why this is working.
So my question is kind of off topic, but
Go ahead.
the horizontal asymptote, wouldn't the degrees, like last time you did, like if the degree is 1 over 1 equals 1?
No. So if the degree is 1 over 1, the horizontal asymptote is the fraction of the coefficients. So here the degree was 1 and 1. They were the same degree,
Oh.
and it's the numbers out in front that give us the horizontal asymptote. Sorry, where here? That says, so that says as x goes to infinity, or as x is getting larger and larger and larger. And I'm not saying these words, but this is, we're kind of talking about the idea of a limit here. We're saying this function is getting close to this value as x is getting large. And you're definitely going to talk about that when you take calculus next quarter. Other questions? Okay. So a function will approach, I already said these words, get closer and closer to the slant asymptote for values near negative infinity and or near positive infinity. So let's look at some of the examples that we already know how to answer. This function here. Slant asymptote or horizontal asymptote? Horizontal, because the degrees are the same. The coefficients are 1 and 1. So here the horizontal asymptote is going to be y equal to 1 over 1, which is 1. And let's look at this one here. This one, the degree on top is less. And since the degree on the top is less than the degree on the bottom, the horizontal asymptote is going to be 0. Over here, same, well, not the same, right? For f of x equal to 3x minus 2 over x plus 2, the degree on top and the degree on the bottom are both 1. So the degrees are the same. The horizontal asymptote is going to be y equal to 3 divided by 1, the quotient of the leading coefficients. Lastly, this one up here, the degree on top is 1 larger. That's where we have a slant asymptote. So this one's definitely going to have a slant asymptote, which I usually abbreviate like this. And we have to do the polynomial division to find it. So we're going to have x minus 1 divided into x squared. And I'm going to write plus 0x plus 0 to help me do the division. So let's see. What do you multiply by x to get x squared? X. X times x is x squared. X times negative 1 is negative x. Subtract. X squared minus x squared is 0. 0x minus x is plus x. I will tell you most of the mistakes I see in finding the slant asymptote come from missing the minus at like not doing the minus a minus. So definitely be super extra careful when you're doing the subtraction part of the division because it's where the most mistakes usually happen. Bring down the 0. X times what gets me x? 1. 1 and done, right? We are done there because we have got a constant. So once you get to the constant on top, stop. That's it. Y equal to x plus 1 is my slant asymptote. And just like other asymptotes, we are going to, that's what I'm looking for. We are going to draw them as a dashed line. Somebody asked, it's a good question, can we do synthetic division? The answer is yes, sometimes. Meaning, for this problem, you could totally do synthetic division, but if you're but like, for example, for this first one we did here, you can't do synthetic division for that because you can only do synthetic if your denominator is like x minus 2 or x plus 5. If it's more complicated than, like if it's a higher power, you can't use synthetic. I would encourage you to do it long ways, but if you want to use synthetic for the ones you can use it for, you're sure. If you don't know what synthetic division is, don't worry about it. It's not my favorite. It is useful sometimes, but you're going to want to be able to do the long division the long way when you do Calc 2, because it actually does become important to see what all the pieces are. So yes, synthetic if you want to, but I would encourage you to do long division. Okay. I believe these templates are available on Canvas. I can certainly look to make sure that's true, but you don't have to use them. You can use them if you want to. If you factor the no, you cannot. If you factor the denominator, you cannot use synthetic. Synthetic only works if your denominator is a linear function of x, like x plus 5 or x minus 3. All right, so we're going to graph f of x equals x cubed over x squared minus 9, and we already know just by looking at it, it has to have a slant asymptote because the degree on top is 3 and the degree on the bottom is 1 less than that. So we're going to do that on notes. So let's find the slant asymptotes. We're going to do x squared. I also want to get my intermediate terms for x squared. So I'm going to do x squared plus 0x minus 9 divided into x cubed plus 0x squared plus 0x plus 0. The nice thing about this is it's only a two-step process usually, because you're going to have the first x part and then you're going to have the second constant part, and that's kind of it every time. X squared times x is going to get me x cubed plus 0x squared minus 9x. Subtract 0 minus 9x is 9x. Okay, now here's a question you have to be careful about. What do you multiply by x squared to get 9x? Well, there is an answer, but I don't want it. Because if the power here is less than the power there, I'm done. It means there would have been a plus 0 here for an x part. Right? There isn't any constant you can multiply by x squared to get 9x. So since this is a lesser power, we stop. So our slant asymptote here is just y equal to x. Which means when we start drawing this thing, we're going to have an asymptote like that. And then the rest of the stuff is the usual kind of stuff for drawing a rational function. We're going to find the y-intercept, the x-intercepts, the vertical asymptotes, the horizontal asymptote. Well, we're not going to look for a horizontal asymptote because you can't have a slant and a horizontal. So if you've got a slant, you don't look for horizontal, and vice versa. If you've got a horizontal, you don't look for a slant. So y-intercept, we're going to set x equal to 0. If x equals 0, we're going to get f of 0 equal to 0 over 0 minus 9, which is 0. Great. X-intercepts, set the function equal to 0. X cubed over x squared minus 9. But we know when we set the function equal to 0, that's just going to be resulting in setting the numerator equal to 0. You could multiply both sides by the denominator, you get x cubed equal to 0. And then we're going to get x equal to 0. And you guys all want to tell me the multiplicity is how much? Yeah, it's 3. Because it was x cubed equal to 0. Vertical asymptotes, we're going to set the bottom equal to 0. Okay. X squared minus 9 equal to 0. I really do recommend factoring here, right? I know you could set x squared equal to 9 and solve and get x equal to plus or minus 3. But I think you're going to be better off if you write it as x minus 3 times x plus 3 equal to 0. And you're going to get x equal to 3 and x equal to negative 3. You can do this number line thing. You don't have to. It's not unworthwhile. On your number line, here's what's going to go on the number line. Any x-intercept, any vertical asymptote. Because those are the places where the sign can change. So let's look at our original function, which I might look back at and factor and write it as x cubed over x minus 3 times x plus 2. And the reason for factoring this is because it makes it easier to determine the sign when you plug in a number. If you're just multiplying things, it's really easy to see what kind of sign you're going to get. Whereas if you're adding things, it's less clear. So if I plug in a number like 4 cubed is positive, 4 minus 3 is positive, 4 plus 3 is positive. And a positive divided by a positive times a positive is still positive. If I pick a number like 1 cubed is positive, 1 minus 3 is negative, 1 plus 3 is positive. So I have a positive divided by a negative times a positive, which is negative overall. 0 came from this x-intercept with an odd multiplicity, so we know we're going to cross the x-axis. So we're going to change signs. Or you could pick -1 and plug it in and see that it's negative, negative, positive. And then finally, over here, if I pick something like -4, a negative number cubed is negative. -4 minus 3 is negative. -4 plus 3 is negative. And a negative divided by negative times negative is negative. Alternatively, you could have looked at the multiplicities of all the things, meaning the vertical asymptotes and the x-intercept, and seen that they are all odd multiplicity, which means you're going to change signs every time you go over one of those things. They are dancing. So let's look at the graph. I'm going to put x equal to 3 as a vertical asymptote. And x equal to -3. Which kind of nicely lined up here. And then we're going to try and draw the graph. And while I might usually start, no, that's not true. I wouldn't usually start there. I'm going to start at my x-intercepts / y-intercepts. I only have 1 point, right? I only have 1 point. That's kind of terrible. So luckily, we have this sign chart. So we know that to the between 0 and 3, the function's negative. So we kind of have to go down this way. We have no other choice, right? When you get close to a vertical asymptote, you either have to go down to negative infinity or up to positive infinity. There are no other options around vertical asymptotes. On the other side of this vertical asymptote, the function's positive. So instead of being way down to negative infinity, it's going to be way up to positive infinity. And then what's going to happen? Well, this slant asymptote is telling us as you go way out this way, the function is going to get closer and closer to that asymptote. Right. And same kind of deal to the left. In fact, this function is an odd function. It has rotational symmetry. So we can expect everything that happened over here to get kind of reflected or rotated over and happen over here. We're going to go up this way like that. Right, we have to because the function's positive between 0 and -3. I'm usually graphing things by lack of choices. I'm just like, what do I have to do? Well, I can't do anything else. I have to go this way because I was told to. I can't go a different way. And then over here on the other side of this vertical asymptote, we have to be going on the negative side of the x-axis because we know it is. So we're going to be way down here. And I kind of put that negative, probably not a great spot. Sorry. And then as we move further left, we have to get closer and closer to this slant asymptote. And in calculus, you will definitely learn how to find where this bottom part is here and where this top part is here. We don't have the tools, so we just make it up at this point. You don't have to turn around because you have to get closer and closer to the slant asymptote, but that's kind of it. There's nothing else to do other than just draw it like we think it might look like. I do want to mention, just like with horizontal asymptotes, a function can totally cross its slant asymptote. This function definitely crosses its slant asymptote right at the origin. Totally allowed. Questions?
Like, how do you, I guess, like, decide exactly how the, I don't even know how to describe it without like the top right curve.
Yes.
Why is it there rather than just on the right side?
Like, why isn't it like over here?
Yeah.
So the reason it's not like, so for example, I'm gonna, I don't want to, yeah, sure. Let me just, I'll take this old one here. Sure. So the reason it's not here, right, is because a couple things. I don't have an x-intercept. And I know I have to be, well, we already saw that it had to be positive over here. So it has to be, it can't be down here, it has to be up this way. So I'm using the fact that it's positive on the right side of this vertical asymptote. Say, well, okay, I'm going to say this very, very definitively. When you get close to a vertical asymptote, the function has to do one of two things. It either shoots up to infinity or down to negative infinity. Oh, I forgot to find my video. I mean, not that you guys really care, but the people online might care. Sorry, you can't see me doing the things. Let me say that again. When you have a vertical asymptote, the function either has to go up to infinity or down to negative infinity. There's no other choice. I knew it couldn't be down to negative infinity here because I know that the function's positive over here. So it had to be up to positive infinity. And then as I move further right, the only other thing that's kind of telling me what to do is this slant asymptote. It's saying, oh, we get closer and closer to that as we move further and further right. So those are the kind of the directives that are informing what I'm doing.
And then the -1/8 shows that it's on the typical.
Oh. Sorry, this part over here?
Yeah, yeah.
So I plotted this point, and like when I graphed this one the previous time I did this, I didn't do the number line.
Oh.
What I did instead was I plotted a point. I said, well, if I plug in 1, I'm going to get a negative value. So I'm going to get a point right there, which is telling me, oh, it's got to be going downwards, because then I don't have any other choices.
So it sounds like you haven't been paying attention.
No, it's all right. I don't think you haven't been paying attention.
Like
I'm not sure what you mean by the
okay,
reciprocal.
I don't like the one that looks exactly like the one on top, but it's
This one down here, this reflection down here.
yeah.
So I'm using the same information. So our sign chart was this. So I know that just like how this one had to be positive, so it was going up to positive infinity, over here on the left side of -3, the function had to be negative. I cannot be up this way because it's negative. It has to be down this way. And then the same sort of thing. As we move further to the left, we are forced to get closer and closer to this slant asymptote. Good question. I mean, and I don't think you're not paying attention. All right. Other questions about this one before we do more examples? It's going to be the same process like every time. We're going to do the same things and ask the same sorts of questions to ourselves. Let's look at this next one. F of x equal to x squared minus 4 over x minus 1. Definitely has a slant asymptote. You totally could do synthetic division on this one if you wanted to. I'm not going to do that because it's not my jam. But if you like it, do it. So let's see, we've got x minus 1 divided into x squared plus 0x minus 4. Right? I want all those missing powers of x. X times what gives me x squared? X. X times x is x squared. X times minus 1 is minus x. Subtract. X squared minus x squared, of course. 0x minus minus x is x. It's 0x plus x. X goes into x one time, and we're done. Here's my slant asymptotes. So when we graph that slant asymptote, again, the asymptotes are not actually part of the graph. Right? They're guidelines for graphing, but they're not actually features. I mean, they're features. Okay. When I graph this line, y equals x plus 1, I know it's going to have a y-intercept of 1, an x-intercept of -1. And then I'm going to draw a dashed line through those 2 points. Like that. I'm going to wait to label it because I can. Just like with horizontal asymptotes, slant asymptotes have no effect on what's happening in the middle. The function can look super crazy in the middle, and then as you move way out to the right, well, we're gonna graph this one on Desmos so we can actually look at it. It's gonna get closer and closer to this line. So, yeah, let's do all the things. Y-intercepts, set x equal to 0. Oh, sorry, thank you. F of 0 is gonna be 0 minus 4 over 0 minus 1, which is positive 4. Great. And I do recommend kind of plotting things as you go. It's not a bad idea. So there's 0, 4. And then x-intercepts, we're going to set just the numerator equal to 0. And again, you can set the entire function equal to 0, x squared minus 4 over x minus 1. And that's just going to become x squared minus 4 equal to 0. Why is that again? Because I'm multiplying both sides by the denominator. The left side just becomes x squared minus 4. The right side is 0 times x minus 1, which is still just 0. Again, you know me, I like to factor. X minus 2 times x plus 2 equals 0. So we're going to get x equal to 2 and x equal to -2. Both with what multiplicities? Both of the multiplicity of 1, meaning they're going to cross at both of those x-intercepts. Vertical asymptote, set the bottom equal to 0. We're going to get x equal to 1. Also with an odd multiplicity. How it was odd because there wasn't a power. right? If you don't see a power, the power was 1. You could really write this. I know it's kind of silly, but you'd say, oh, that's x minus 1 parentheses to the first. You don't need that. We don't write that, but that's what's happening there. Yeah, sign chart. Okay. The sign chart's not terrible. It's just not my favorite thing to do. So, oops, I kind of did. Fine. So there's the numbers that go on my sign chart. Every intercept, every vertical asymptote. All the x values, right? The x values are the intercept, the vertical asymptotes. Sorry, the x values are the x-intercepts and the vertical asymptotes. The y values are the y-intercept, and if you had a horizontal asymptote, that would be one. So on my number line, intercepts, asymptotes, and I'm just going to look at the signs. So I pick a number larger than 2, like 3, and plug it in. The top's positive, the bottom's positive. Pick a number between 1 and 2, like 1.5. The top is definitely negative. 1.5 squared is definitely smaller than 4, and the bottom's definitely positive. Pick a number between negative. I already have a number between negative 1 and 2. Sorry, 1 and negative 2. I have 0. If I plug in 0, the whole thing's positive. And then if I pick something less than negative 2, like negative 3, negative 3 squared is positive 9. Minus 4 is positive. Negative 3 minus 1 is negative. So it's negative there. Just like last time, it's changing every time. It's going above, below, below. If I'm going from right, if I'm reading from right to left, which I know is not how we always do things, but it's just what I have to do. We also could have just used the multiplicities, right? Said, okay, we know at x equals 2, it's going to cross. It's going to go from positive to negative, and then negative to positive, and then positive to negative. So let's draw the things. I didn't quite line these up perfectly. The vertical asymptote's at 1. And my intercepts are at positive 2, negative 2. Okay. Let's try graphing this from left to right. Although I will be frank, here's what I would do if I hadn't done this number line thing here. I would have plotted all these points of these asymptotes. And then I would have started right there at the y-intercept and asked myself, as we move to the right towards this vertical asymptote, which way are we forced to go? Are we forced to go up, or are we forced to go down? We are forced to go up. What's preventing us from going down? It's not the slant asymptote. What's preventing us from going all the way down here? There's no x-intercept. Can't cross the x-axis if you don't have an x-intercept. So we are forced upward. That way. And if you move to the left, well, we have to go left and hit that point, and we have to move further left and get closer and closer to the slant asymptote. Or alternatively, we can look at the sign chart. Be like, oh yeah, between negative 2 and positive 1, the whole deal is positive, so it's above the x-axis. And to the left of negative 2, the whole deal is negative, so it's below. It has to be getting closer and closer to the slant asymptote. Then on the other side of this vertical asymptote, you can either use the sign chart you've made, or you can say, well, I know the vertical asymptote has an odd multiplicity. And when vertical asymptotes have odd multiplicity, one side's up and one side's down, or they're opposite, as I like to think of it, right? Odd multiplicity, opposite behavior. So if this side's up, this side has to be down. And then we're going to come towards this x-intercept, cross, and then get closer and closer and closer and closer to the slant asymptote. And again, right, we could have used the sign chart. Said, oh yeah, it's negative between negative 1 and, sorry, positive 1 and 2. And then after 2, it's going to be positive forever and ever and ever. And I do think it's worth noting. Come on, let's take your time. That this function, y equal to x squared minus 4. Right in the middle, okay, like it looks like stuff's happening, But if you zoom way out, it really just starts to look like that line y equals x plus 1. And that's kind of the whole deal. Is in the middle, sure, whatever can happen. But as you move way away from the middle, as x gets really, really large or really, really negatively large, the function just looks like the line y equals x plus 1. No, they're not exactly the same. They're never actually exactly the same, but they're very, very similar the further you move from the middle. That's the idea with the slant asymptote. And you can, if you zoom back in a bit, oh, my cursor, where'd you go? But you can kind of start to see the separation of them. Okay, yeah, they're not the same. And in the middle, they look very different, but like as you move way out, they're really looking very, very similar. Okay. Cool. Time is it? Okay, we got time for one more example. Let's look at this one. We're going to graph f of x equal to x minus 2 cubed over x squared minus 5x plus 6. Oh, yeah, okay. So this one has an, oh yeah, question. So, actually, I'm not sure what you're saying exactly. No, it could be x minus something. It just depends on how the division works out. This one actually is going to be a minus. So yeah. So here's an important thing to see. Before you do any of this, and I know we haven't been doing this because we haven't needed to. Before you do any of this, you should see if any of the factors cancel. So I'm going to write this out. This is equal to x minus 2 cubed. And the denominator does factor as x minus 2 times x minus 3. I know I wrote it the other way, but okay. Yeah, that's totally fine. Go to your appointment. Yes. So we can cancel a factor of x minus 2 here. This is going to equal x minus 2 squared divided by x minus 3. So what's that going to mean happens at x equal to 2? Well, it's going to be kind of weird because if you plug in 2 here for x, you get 0 divided by -1, which is just 0. You would totally have an x-intercept in 2 here. But if you plug in 2 here to the original, you get 0 divided by 0, which is undefined. So what we're going to have, what's going to happen is when you factor, or when you cancel a factor like this, the x value that would have made the thing equal to 0 over 0, 2 in this case, we're going to have a hole at 2. This graph has a hole at x equal to 2. So we know we have a hole because we canceled the factor of x minus 2. So we could have gone through the additional step of writing this as x minus 2 squared times x minus 2 over x minus 3 times x minus 2. And then one of those x minus 2s cancels out. So when you cancel a factor in the top and the bottom like that, so we canceled x minus 2, that means we have a hole at x equal to 2. Yeah. Well, how many times does 0 go into 0? 7. 20. 36. We're all right, which means none of us are right. Right, like in The Incredibles, when everyone has superpowers, we know, right? Okay, yeah. But the answer is right. So really, I should be more specific with my undefinedness. 0 over 0 is actually what's called an indeterminate form, meaning it can literally take on any value. Literally. And you're going to see a lot of this next quarter because a lot of the limits you deal with when you're talking about finding derivatives, in fact, almost all of them are 0 over 0 types of things. So 0 over 0, but it's indeterminate because really the answer to the question is it could be anything, right? 0 divided by 0 could be 5. 0 goes into 0 5 times. Do the division, subtract. Oh yeah, you get 0 for your remainder. Check. But really the answer is right. There's no answer. So yeah. Well, because so here's the thing. Any value right next to 2 is going to be perfectly well defined. Like if you plugged in 2.1 or 2.01 or 2.0001, everything there is going to be right on. But at 2 is where this thing's going to look kind of funky. How much time have we got? Not enough. So, yeah. Let's work through this, and I'll talk about it more at the end. Okay. So we're gonna treat this graph like this graph. So our function f of x is x minus 2 squared over x minus 3, with the caveat that x is not allowed to equal 2. Because if x were equal to 2, it would be undefined. Okay. So let's find the usual stuff. Y-intercept. We're going to set x equal to 0. We're going to get f of 0 equal to 0 minus 2 squared over 0 minus 3, which is positive 4 over negative 3, or negative 4/3. X-intercept is going to be kind of dicey, because if we set the whole thing equal to 0, we're really just setting the top equal to 0. But if we set the top equal to 0, what are we going to get? Well, yeah, because we're going to get x equal to 2, but we know not okay. So we're actually going to, there would have been an x-intercept at 2. We're going to have a hole there instead. So we're going to have a hole on the x-axis. Vertical asymptote. Set the bottom equal to 0. We're going to get x equal to 3. We have to do the polynomial division to find the slant asymptote. There is a slant asymptote. In this reduced form, the degree on top is what? And the degree on the bottom? Oh, it's exactly 1 larger. So we're going to multiply at the top. X minus 2 squared is x squared minus 4x plus 4. So then the division we're going to do is x minus 3 divided into x squared minus 4x plus 4. X times x gives me x squared, so x times x squared. X times negative 3 is minus 3x. Minus 4x minus a minus 3x is minus 4x plus 3x, which is minus x plus 4. X goes into minus x, negative 1 times, and we're done. That's my slant asymptote. Y equals x minus 1. Okay, we have all the things we could get. We have our intercepts, we have our asymptotes. There's nothing left to find. All that's left to do is to try and graph it. Oh, I suppose I could do the sign chart. I can do the sign chart. So the important points to include would be the x-intercept, even though it isn't actually a point on the graph, it's undefined there, it's still a place where the sign might change. So I'm going to include x equal to 2 and x equal to 3. I should have put the 3. Okay, fine. Looking at my expression here, to pick a number larger than 3, like 4, positive on the top, it's positive on the bottom. Pick something between 2 and 3, like 2.5. The top is always positive because it's something squared, and 2.5 minus 3 is definitely negative. If I pick something less than 2, like 0, because I've already done the y-intercept, I know when I plug in 0, the whole thing's negative. So this thing's going to be below, then above. So let's graph the things we know. So I've got a vertical asymptote x equal to 3. I've got a y-intercept at negative 4/3. And there would have been an x-intercept at 2, 0, but it's a hole. Okay, so let's graph it. So we know it's negative to the left of 2 and negative after 2. So it's going to be, oh, I forgot one thing. I forgot the slant asymptote, which is the line y equals x minus 1. So that would have a y-intercept of -1 and an x-intercept of +1. It would look like that. Okay, yeah, it's an important feature, right? Okay. So now, what I think is going to happen is we're going to be negative. We're going to come towards the hole there, and then we're going to bounce off and stay negative. And then on the other side, we're going to become positive. We're going to be way up here. It's going to look like this. It's not negative x, it's x minus 1. Yeah. No, yeah, you're totally right there. You could get a slant asymptote that was like y equals negative x plus 2 or something, and then it would go the other way. Bouncing off here, going down to negative infinity, and then on the other side of the vertical asymptote, the function's positive, so it has to be up to positive infinity. And then it turns around at some point and continues onwards towards the slant asymptote. Okay, so this graph has a hole right there, which means it's just undefined right there. But if you plugged in something like 2.1, in fact, okay, if x equals 2.1, y is going to equal, if I plug it in, 2.1 minus 2 is 0.1 squared over negative 0.9, which is pretty negatively small, right? It's 0.01 over negative 0.9. That's like 1/90th, negative 1/90th. So we're very, very close to 0 if you move just a little to the right or a little to the left. I think I'll make a short little video today with a couple more examples, just because I feel like I would like to show you one more, an easier example with a hole. But here's the short answer takeaway. If you have a factor that cancels like this, you're going to have a hole at the point that would have made it 0 over 0. And when I plug, and so then if you plug in 2 to the factored and canceled form, if I plug in 2 there, what do I actually get? 0 over not 0, which means it's equal to 0. So we do have a hole at the point 2, 0.